Hi Year 12. This is our third lesson for the topic of differential equations. In this lesson, we're going to look at first order differential equations. So far we've covered ordinary differential equations, including initial value problems. And last lesson we looked at slope fields. So what happens if we have a differential equation in terms of the dependent variable? We can't take integrals of both sides with respect to x, because on this side I would end up with the integral of y dx, and the variables wouldn't match. But there is an easy solution. We take reciprocals of both sides. So instead of dy dx, I have dx dy. Now when I take the integrals of both sides, I do it with respect to y, like this. You see how the variables match now? So I end up with x is equal to the integral of 1 on y dy, which is log base e of y plus c. Now I want to make y the subject, so I'm going to take this constant over the other side, and now I'm going to change that into index form. And so y is equal to e to the power of x take away c. Here's another example. Solve dx dt equals x squared, given t equals 1 when x is equal to 1. Again, you can see I have the dependent variable. It's easy to tell because if I take integrals of both sides with respect to t, they're not going to match on this side. So let's do reciprocals of both sides. dt dx is equal to x to the negative 2. And taking integrals of both sides with respect to x, I end up with t is equal to the integral of x to the power of negative 2 dx. Integrating gives me negative x to the negative 1 plus c. Now let's resolve the constant before we change and make x the subject. When t is 1, x is 1. And that means that c is equal to 2. So t is equal to negative 1 on x plus 2. And turning this around to make x the subject, I get x is equal to negative 1 all over t take away 2. Here's a past HSC question. Solve dy dx equals e to the 2y, finding x as a function of y. All right, so again we can see we have the dependent variable. So taking reciprocals of both sides, dx dy is equal to e to the negative 2y. Now integrating both sides with respect to y, x is equal to the integral of e to the negative 2y dy. This is a chain rule. Now outside function is an exponential, inside function is a power rule. So we're going to end up with, the exponential stays the same, divide by the derivative of the inner function, which is negative 2 plus c. Now it says find x as a function of y, so we actually don't have to change this to make y the subject. But I'm just going to tidy it up a bit. So x is equal to negative e to the negative 2y over 2 plus c. Now when we're given a differential equation of the form dy dx is equal to a function of x multiplied by a function of y, we use a method called separation of variables. It's a really cool technique. So have a look at this question here. If we write it like this, you can see that it is a function of x multiplied by a function of y. Now what we do is get the y variables together and the x variables together by cross multiplying. That doesn't make a lot of sense what I've written here. We really need the integral sign. So we have the integral of y dy is equal to the integral of x dx. So now all we do is integrate this side with respect to y, which is y squared on 2, and this side with respect to x, which is x squared on 2. Now we only need to add one constant. We don't need to put a plus c on this side as well. Now tidying this up and turning it around, we end up with x squared take away y squared equals 2c. We don't actually need to write 2c because 2c is just a constant. So our final answer will be x squared take away y squared is equal to some constant k. Now not all differential equations can be separated. We need a function of x multiplied by a function of y. So which of these can be separated? This first one can't. We have f of x plus g of y. This one's okay. This is f of x multiplied by g of y. And this one's okay as well, because we could write it like x multiplied by 1 on y plus 1. Here's f of x, here's g of y. Let's have a look at some examples. Solve dy dx is equal to 2xy. So we can see we've got a multiplication of two functions. One involves x, one involves y. So separating the variables, the y comes over here like this, and the dx comes over here. And don't forget your integral signs. All right, integral of this is log base e of y, and the integral of this is x squared. And so I'm going to have ln of y is equal to x squared plus c. Now I'm going to make y the subject. So I'm just going to turn this out into index form. So y will equal e to the x squared plus c. Example 2, solve f dashed of x is equal to x cubed over y plus 1 if f of 1 is equal to 0. So having a look here, we have what we need to separate the variables. This is x cubed multiplied by 1 on y plus 1. Now, this notation doesn't really help us, so I'm going to actually change that to be dy dx. Now let's separate the variables. So the y plus 1 comes up over here, the dx comes up over here. Include your integral signs. And now let's integrate. On the left-hand side, we have y squared on 2 plus y. And on the right-hand side, we have x to the power of 4 on 4 plus c. Now we're going to resolve this constant. So substituting in when x is 1, y is 0, I end up with c being negative a quarter, which gives me y squared on 2 plus y is equal to x to the power of 4 on 4 take away a quarter. Now if I want to make y the subject and I have a y squared term and a y term, my only option is to complete the square. But I don't really like this 2. I want to get rid of it, so I'm going to multiply every single term by 2. That gives me y squared plus 2y is equal to x to the power of 4 on 2 take away a half. Now let's complete the square. Locate the term in y. The coefficient is 2. Halve it, square it, gives me 1. Add 1 to both sides. So now I can complete the square here, and just tidying this up, I'm going to get x to the power of 4 over 2 plus a half. Now completing the square, this is y plus 1 all squared, and I'm just joining this together, equals x to the power of 4 plus 1 all over 2. Take the square root of both sides, don't forget your plus or minus. And taking the 1 over, I get y is equal to negative 1 plus or minus the square root of x to the power of 4 plus 1 all over 2. Now we have two solutions here, and only one of them goes through this point. And we need to figure out which one it is. So I'm going to test that point 1, 0. I'm going to substitute in x equals 1, like this. Now 1 plus 1 is 2 over 2 is 1. Square root of 1 is 1. So which one of these is going to give me y is equal to 0? Can you see it's the plus, negative 1 plus 1? So the particular solution is y is equal to negative 1 plus the square root of x to the power of 4 plus 1 all over 2. And here's one more example. Y dy dx plus y squared sine x equals 0. Now this one looks a lot different to the ones we've been doing, but let's start by making dy dx the subject. We'll take this term over the other side. So y dy dx is equal to negative y squared sine x. Divide both sides by y, and note that y can't equal 0. And look, we have a function of y multiplied by a function of x, so we can separate the variables. The y comes over this side, 1 over y dy. I'm going to leave the negative there, but it doesn't really matter. You could take it over as well if you wanted to. Negative integral of sine x dx. Now, you'll note that it's obvious that y can't equal 0 because it's on the denominator here, so this is no longer important. Now, let's integrate both sides. We end up with log base e of y is equal to negative multiplied by negative cos x plus c. And then finally, making y the subject, we're going to get y is equal to e to the power of cos x plus c. Now the position and the timing of the constant is important. We can't just ignore it and add it in at the end. I'm going to return to this question, dy dx equals 2xy. Let's separate the variables, integrate, make y the subject, and then add the constant in at the end. Well, is that correct? Let's have a look at our solution from before. Integrating both sides, learn y is equal to x squared plus c, make y the subject. Is this the same as this? Let's use our index laws. This is e to the x squared multiplied by e to the c, and this is a constant. Let's call it a. So can you see that the constant is actually a multiplier of e to the x squared? It's not added on at the end, so these are not the same thing. So add your constant in. If you have to resolve it before you make y the subject. Let's finish off with a past HSC question. Find the curve which satisfies the differential equation dy dx equals negative x over y and passes through the point 1, 0. So we can see that we can separate the variables. So we're going to start by moving the y over this side and the dx over this side. Integrate both sides, I get y squared on 2 is equal to negative x squared on 2 plus c. Now let's resolve the constant. So substituting in x is equal to 1 and y is equal to 0, I end up with c is equal to a half, which gives me y squared over 2 is equal to negative x squared over 2 plus a half. Multiplying every term by 2, I get y squared is equal to 1 minus x squared. And so y is equal to plus or minus the square root of 1 minus x squared. Now if I substitute the point 1, 0 back in, I can't tell any difference between the plus and minus because it's going to be 1 minus 1, which is 0. So I'm going to leave this as a relation. But I do recognise that it is the unit circle, so I could write it in this form or in this form. Now here's what the markers said. Areas that students need to improve. Understanding that differential equations should not be integrated where there are multiple variables on one side. Avoiding placing constants of integration on both sides, as this can cause confusion when evaluating the constant of the primitive. And focusing on algebraic skills when dealing with negative numbers, particularly when substituting and solving equations. Okay, that's it. In our last lesson for this topic, we're going to look at modelling differential equations.